Hello everyone, my name is Stratis Matsukis. I work as an electrical and computer engineer at GTech Medical Engineering, and I'm also doing my PhD at Johannes Kepler University. Today I will present our work on developing a novel 64-128 channel amplification system with 4 independent bias voltages for recordings using graphene resistor arrays. In the field of neural engineering, an ongoing challenge is to improve neuroelectronic interfaces for increased spatial resolution and sensitivity. Historically, the development of the technology has led to advances in neuroscience several years later. For example, the invention of tetrodes in 1983 led to the discovery of single neuron representation of individuals in 2005. Similarly, the development of the Utah array in 1990 resulted advances in neuroprosthetics for tetraplegic patients in 2006. Advances in materials have led to the development of active sensors, which are more effective at improving spatial resolution than passive sensors. As sensor size decreases, impedance increases, which in turn decreases the signal-to-noise ratio (SNR). Active sensors address this issue by placing the amplification electronics close to the measurement site, thereby maintaining a high signal SNR. Electrolyte gate transistors (EGTs) advance this technology by integrating sensing and signal processing into a single device. They use an electrolyte to modulate the semiconductor's behavior, converting biological signals into stable electronic ones. In this direction, graphene solution-gated field effect transistor (gSGFETs) offer several advantages, including flexibility, biocompatibility, high carrier mobility, chemical stability, and mechanical conformability, making them highly promising for advanced bioelectronic applications. Recently, gSGFETs have demonstrated their effectiveness in broadband recordings, including frequencies below 0.1 Hz, with results comparable to those obtained with glass micropipettes. Their potential for high-resolution mapping makes them particularly suitable for studying infralow brain activity, which is relevant to conditions like epilepsy. To enhance the use of gSGFETs in electrophysiological recordings and support their validation and development, we have developed a robust, high-fidelity, and flexible multi-channel amplifier system. Our advanced 64-128 channel system supports the simultaneous recording of 64 AC and 64 DC channels with the capability to use 4 independent bias voltages. A gSGFET consists of a thin graphene layer positioned between two metal contacts, source and drain, with a reference electrode immersed in an electrolyte. When voltage is applied to the reference electrode, it generates an electric field within the electrolyte, modulating the graphene's conductivity by causing ion accumulation near its surface. This enables precise control of the current flowing through the graphene. Due to graphene's high carrier mobility, gSGFETs are highly sensitive to gate voltage changes, making them ideal for neural interfaces. To use gSGFET as recording probes, electrical characterization in saline solution is necessary. The transistor transfer curve (IV characterization) measures the drain source current (IDS) at a fixed drain source voltage (VDS) as a function of gate voltage (VGS). This process extracts key parameters like transconductance, and it's required before each experiment. A basic circuit for interfacing the gSGFETs was presented by Herbert and others, providing current-to-voltage conversion and separating signals into DC and AC components for each channel. This was combined with commercial electronics in some initial experiments. To further advance gSGFET technology for neural encoding, we developed a customized 16-32-channel system. This system included a preamplifier box for signal processing, a DAC box for bias adjustment, and a battery system for an isolated power supply. Final amplification was achieved using a custom version of the G-Hyam amplifier capable of handling both AC and DC signals with a MATLAB Simulink interface for characterization and recording. This system was used in experiments that led to several pioneering applications. Despite the success of the 16-32-channel system, several factors drove the development of a new system. First and foremost was the need to significantly improve spatial resolution, a critical factor in neural engineering. Another key goal was to incorporate support for multiple bias voltages, enabling the system to accommodate various electrode types, including intracortical and epicortical electrodes. To facilitate the transition from preclinical to clinical applications, it was crucial to integrate separate components such as the DAC box, preamplifier box, and battery system into a single, cohesive unit that meets medical standards. Several improvements were also made based on the previous 1632-channel system. A major enhancement was reducing dramatically the time required for DC-IV characterization, which is vital in the in vivo experiments where time is critical. All these needs were addressed with a new 64-128 channel system which supports arrays of 64, 32, or 16 channels and features 4 different bias voltages. The main components of this system include the gSGFETs breakout board, preprocessing device, amplifier, and software interface. The amplification system begins with the breakout board where up to 4 HDMI cables connected to gSGFETs arrays, each carrying a different bias voltage. This setup allows for flexible configuration, including combinations of 16 or 32 channel arrays with varying bias voltages or a single bias voltage applied to a 64 channel array. HDMI cables are chosen for the robust shielding, which effectively minimizes signal interference. They also provide high data bandwidth, ensuring quality signal transmission. For output through the preprocessing device, a 65-pin LEMO cable gathers signals from the 64 drains. Additionally, a custom cable delivers 4 precise bias voltages, ensuring the system operates accurately across different configurations. The preprocessing device is the heart of the 64-128 channel system, primarily responsible for converting and preamplifying the analog signal, as well as establishing bias voltages for the gSGFETs. Its main architecture consists of a mainboard, 8 analog modules, a digital board, and an accumulator board for the power supply. At the core of the system, the main board processes incoming signals from the electrodes through the 8 analog modules and directs them to amplification stage connectors. It also regulates power distribution, generating plus 5 volts ground and minus 5 volts from a 12-volt supply. Each of the 8 analog modules is responsible for handling 8 channels, converting signals from current voltage and splitting them to DC and AC components. This flexible design supports various electrode arrays and electrode types, intracortical or epicortical, by providing different VD and VS voltages as required. The digital board, functioning as the brain of the system, is equipped with a Bluetooth module and a microcontroller to wirelessly receive settings for VS and VD voltages, converting them into analog signals through 8 digital to analog converters. It also controls bypass switches during electrode characterization, reducing response times by avoiding large time constants. The preprocessing device efficiently manages signals from the graphene transistors, outputting 64 AC and 64 DC channels to the next stage of amplification. The amplification stage of our system features the Graphene device, a customized version of the well-established G-high-amp amplifier from GTEC Medical Engineering. The Graphene offers 108 and 28 input channels with 64 channels dedicated to AC amplification and 64 channels for DC amplification. This setup ensures both dynamic and steady-state signals are captured with exceptional clarity. The amplifier delivers high signal resolution at 24 bits, supports sample rates up to 38 kHz, and offers broad input sensitivity of plus minus 250 millivolts. In addition to the firmware developed for the hardware devices, a substantial amount of software was created for the user interface. The recorded signals are transferred to a computer via a USB cable, where the system interface developed in MATLAB and Simulink manages the data. Two similar models were created for user interface, one for the characterization of the gSGFETs and another for conducting the recordings. In the DC characterization model, the researchers can initiate the electrode characterization process. To start, they must configure the Bluetooth communication settings, select the appropriate amplifier, and specify the sampling rate within the recording settings. Users also define the sweep VGS settings, including start and stop voltages, step size, sweep duration, and VDS voltage. Once the run button is pressed, four distinct IV current curves are generated for each bias group. After characterizing the transistors, researchers can bias the transistors to their optimal operating points and begin the recording process. This model supports the visualization and recording of both AC and DC signal components. Users need to configure Bluetooth communication settings, select the appropriate amplifier, set the sample rate, and define the VGS and VDS voltages for each of the four groups. Once these parameters are configured, the recording process is initiated by pressing the run button. The model features four scopes, each displaying 16 channels for viewing the AC component and another four scopes for viewing the DC component. The recordings are saved in four files, each containing both AC and DC components. By clicking on each scope, researchers can view live signals from each bias group. For system validation, a series of performance tests were conducted using custom hardware and software. These tests evaluated the accumulators, power supply, generation unit, current consumption, bias voltage generation, and noise performance, along with various functional tests. All tests were conducted initially with resistors and subsequently with gSGFETs immersed in saline solution. Until now, much research on graphene transistors has focused on pathological neural events such as cortical spreading depolarizations and seizures. However, the integration of the 64, 128 channel system offers even greater possibilities. We propose that combining this novel amplification system with stimulation system presents significant potential. For example, broadband recording of transcranial direct current stimulation and transcranial alternating current stimulation could be explored to observe the spatial resolution of the fields and subthreshold phenomena revealed by the DC component. Another possibility is combining the system with magnetic simulation methods such as low-intensity RTMS. Graphene's low magnetic permeability could result in fewer artifacts compared to metallic sensors under the influence of time-varying magnetic fields. Finally, a key application is using the system with emerging technologies like magnetoelectric nanoparticles. The system's high spatial resolution, reduced artifacts due to graphene, and broadband recording make it ideal for exploring these materials, which are still in the early stages of research and could benefit from this system for their characterizations. In conclusion, our work has led to the development of a fully functional 64-128 channel 4-bias amplification system for recording with gSGFETs. This system fills the gap in translating the technology to high-quality real-world laboratory electrophysiological recordings and accelerate research on gSGFETs. While research so far has been focused on pharmacological agents, the use of the system with simulation setups, and in particular with magnetoelectric stimulation, will open the way to a new area of research in the field. Thank you a lot.